Welcome back, Math 152. Last time in section 6.1, we looked at the normal distributions and finding the probability if we took a randomly selected person or an individual item out of a population, and we could determine the probability that item's value was less than a certain value, more than a certain value. But it was an individual item. That was the key to section 6.1. In 6.2, we're going to look at if we go out and grab a sample and then took the mean of the sample, how does that mean compare to other means? Can we calculate a probability based on that? So it turns out we can. So here, in this figure, they have population data, and if we've gone out and grabbed these different samples, calculated a sample mean for each one of these, and then we're going to basically look how that sample means from the samples create a sampling distribution. Okay. In real situations, statistical studies involving sampling several individuals, then computing numerical summaries of the samples. Most often, the sample mean is computed. If several samples are drawn from a population, they are likely to have different values of X bar. So you can consider this to be X bar 1, X bar 2, X bar 3, all throughout. But the key is now that each one of these are going to be the same sample size. Because the value of each one of these X bars varies each time a sample is drawn, we can consider X bar as a random variable. For each value of the random variable X bar, we can compute a probability, and the probability distribution of X bar is called the sampling distribution of X bar. So here's kind of an experiment that we can consider to take a look at how this works out. This is a tetrahedral dice, so it's got 1, 2, 3, and then on the bottom you have 4. So if we toss these dice, tetrahedral dice, we're going to come out with these numbers. And if we did like 4 of these things, we'd come up with different numbers on each one, and then we could calculate the mean. So if we rolled the first die, the second, the third, and the fourth, and this is what we came out with, we can do an average based on those. And for this particular outcome, the mean would be 2.5. We can do the standard deviation from each one of these, calculate the standard deviation, and in this case, we come out to 1.118. So this was based on a sample size of 4, because we've done it 4 experiments for each one of these. But what we're going to do now is develop this thing based on tossing this thing 3 times, or having 3 separate dies. We roll them, and we write down what the values are, and then we're going to get these values of 111, 112, 113, the full set of possibilities. So for this case, we can list everything, all the possibilities that we could come out. So this is basically doing a classical probability study where we list all of the possible outcomes in the sample space. This is our sample space. But here, what we're going to do is calculate the mean on all of these. Sometimes they'll occur 1 time, maybe 2 times. Here's a 1.33. Here's another possibility. Okay. So here's all the possible values of the mean if I take the mean of these 3 different versions between 1 and our 4. Okay. So the mean of the sampling distribution, if we did all of these means and then we've added them up, it comes out the mean of these are going to be 2.5, which is basically the same thing as the mean of the population at 1, 2, 3, 4. Okay. So in this notation, what we're saying is that the mean of all of those X bars, the averages of all of the samples, is equal to what would be the mean of just the population. Okay. Here the standard deviation turns out to be the standard deviation of the X bars. This is also called the standard error. We're going to use that term a little bit more later on. But the standard error is basically the sampling standard deviation, and this turns out to be 0.6455, and it's less than what the population standard deviation would be that we calculated previously. So it turns out to be that the standard deviation from the population and the standard error, or the standard deviation of the sample means, is related by the sigma over the square root of n, which is the sample size. So here's the formula of sigma divided by the square root of n. So the standard deviation of the sampling distribution, sometimes called the standard error, is denoted by sigma x bar and equals the standard deviation of the population divided by the square root of the sample size. So that's how they're related. So here's an example, and we're just going to take a look and see if we can figure out how to calculate the mean of the X bars and the standard deviation of the standard error of the X bars. And then what we're going to be able to do is use these values for calculating probabilities of the sample mean. So among students at a certain college, the mean number of hours of television watched per week is mu, the mean, population mean at 10.5, and the standard deviation is sigma is equal to 3.6. A simple random sample of 16 students is chosen for a study of viewing habits. Let X bar be the mean number of hours of TV watched by the sampled students. Find the mean, mu of X bar, the mean of the sample means, and the standard deviations of the sample means, the sigma X bar of the sample means. So the mean of X bar is just what we would expect for the mean. This is the 10.5 for an individual student, 10.5, so we set that equal, and then we calculate the standard error of the X bars as sigma over the square root of n. There's the 3.6 from our population standard deviation divided by the square root of the sample size, and this is it has to be given, and here it was 16 students. So again, consider the tetrahedral die example. The sampling distribution for X bar can be determined from the table of all possible values of X bar. The probability that the sample mean is 1.0 is 1 out of 64. So here was the only way that we could make a mean come up, and that was if we got all three of these. This is the sample size of 3. For sample size 3 was if each one of these rolled out a 1. Again, the only way that I could get a 4 is that each one of those 3 rolled a 4. But in between, it turns out that there's multiple ways to get these things. So here is the listing. If we go through, and we're going to do basically, here's the so we just count them up and then do a relative frequency or the probability. So that would be the 1 over 64. If we added all these things up, there's 64 in this table. 4 times 16 rows. The 164 is the 0.016. The 4 divided by the 64 is only one way to get the 4. So that's the 1 out of the 64.016. And the rest of them, we do the same thing, find the relative frequencies. And here's the probabilities. So we have them all listed out. If we go back and build a histogram from that frequency distribution, if we looked at each individual number, each individual would be just the 1/4. I've got 4 numbers possible. I've got 1, 2, 3, 4. That's basically that piece of it. There's the 0.25, each one equally likely. But now if I built from the previous the sampling distribution, here's what that looks like. There's that 0.064, 0.064 for 1 and 4, and then it goes up to that maximum probability. And each one, if we added all of these probabilities up, like we should in a probability distribution, we get 1 from the relative frequencies. So it looks like, let me pull this back down for a second. Here's what the individuals look like. So this isn't even a normal distribution here. This is a uniform distribution, all on 0.25. But we've sampled and took the sum, and it looks like here we've got a normal distribution. So here's the statement. It says, remarkably, it is true that for any population, if the sample size is large enough, the sample mean X bar will be approximately normally distributed. In other words, the sample mean, the distribution of the sample means will be approximately normally distributed. For a symmetric population like the tetrahedral die population, the sample mean is approximately normally distributed even for a small sample size like n equal to 3. If the population is skewed, you'll need a larger sample size to see the sampling distribution turning normal. Consider the following probability distributions below. So here is our original population distribution, right skewed, positively skewed. And when we go through and do basically build sample, all different possible sample size from the population, we get these distributions. So the sample size n equal to 3 for this, because of the skewness, we see the skewness. We start doing sample size largers at sample size n equal to 10, it almost starts seeing that normal distribution is still skewed. And then here for sample size n equal to 30, it looks pretty normal at that point. So the size of the sample needed to obtain approximately normality depends mostly on the skewness of the population. In practice, a sample size n greater than 30 is large enough. Unless the population is normal, then any size is going to be normal. So the remarkable fact that the sampling distribution of X bar is approximately normal for a large sample from any distribution is part of one of the most used theorems in statistics. That's the central limit theorem. It states that let X bar be the mean of a large, n greater than 30, simple random sample from a population with mean mu and standard deviation sigma, then X bar has approximately normal distribution with the mean mu X bar is equal to mu, the same mean of the population, and standard deviation of the X bars, the standard error of the sample means, would be sigma, the population standard deviation over the square root of the sample size. So when we're building this, we have to take just multiple samples of all the same sizes to get that normal distribution. The central limit theorem applies for all populations, so they can be right skewed, left skewed, non-symmetric. But for a symmetric population, a small sample may suffice. But in general, if the population itself is normal, the sample mean will be normal for any sample size. And to see it for any population shape of the distribution, we need n greater than 30. So here's a few exercises just to get us warmed up of being able to understand if we can use the central limit theorem. So here, a sample of size 45 will be drawn from a population with mean mu is equal to 15. The standard deviation sigma is 3.5. Is it appropriate to use the normal distributions to find probabilities for sample means? And we've got the sample size bigger than 30, so we should be fine. We should be able to do that. So yes, by the central limit theorem, n greater than 30, the sample means has an approximately normal distribution. Here, a sample of size 8 will be drawn from a normal population with mean mu is equal to negative 60. That's fine. Means could be negative or positive. And standard deviation of 5. Standard deviations are always positive. Is it appropriate to use the normal distribution to find probabilities for X bar, the sample means? Here, this is smaller than 30, but it came from a normal population. It was stated, so we can do that. So we can use normal distributions to find probabilities of the sample mean. A sample of size 24 will be drawn from a population with mean mu is equal to 35. Standard deviation sigma is the 1.2. Is it appropriate to use the normal distribution to find probabilities for x bar? Sample size is less than 30. I don't see anywhere where they state that the population is normally distributed, so I would not feel comfortable using that. Okay, so no, since the population is not known to be normal and n is not greater than 30, we cannot be certain that the sampling mean has an approximately normal distribution. So let's basically go through a couple of problems here where we're going to do probabilities concerning sample means. So based on data from the U.S. Census, the mean age of college students in a recent year was mu is equal to 25 years. The standard deviation of sigma equal to 9.5 years. A simple random sample of 125 students is drawn. What is the probability that the sample mean age of the students is greater than 26 years? So we've got a sample size of 125 greater than 30, so we can start developing this based on the normal distribution. I need to, anytime I'm calculating probabilities based on normal distributions, I need the mean and a standard deviation. So these are the sample means, so I have to do my conversion to the mean of the means and the standard error of the means. We compute the mean of the sample means and the standard deviations of the sample means to be the mean of the means is the same thing as the population mean, 25. Standard deviation of the sample means is sigma over the square root of n, 9.5 over the square root of 125. That gives us 0.85, and then we get to go to the tables or technology to find the area under the curve. Area, same thing as probability, same thing as proportion. So here they've ran this through with a normal CDF from a TI. Here's the 26, greater than 26. So here's the left endpoint. The right endpoint was 1e to the 99. The sample mean was still, or the mean of the means was 25, but the standard deviation, the standard error of the sampling means was 0.85, and that came out to be 0.1197. So here we've got some Hereford cattle, are one of the most popular breeds of cattle. Based on data from the Hereford Cattle Society, the mean weight of a 1-year-old Hereford bull is 1,135 pounds with a standard deviation of 97 pounds. Would it be unusual for the mean weight of 100 head of cattle to be less than 1,100 pounds? Now, as an observation, here's the standard deviation. So things being usual would be plus or minus 2 standard deviation if an individual bull was sampled or just taken the weight of. So anything between like 935 pounds up to 1,335 pounds for an individual, plus or minus 2 standard deviations. But here we're taking a average weight of 100 head of cattle. So we have to do the mean of the sample means, the standard error of the sample means, and calculate the probabilities based on that. So here the mean of the sample means would be 1135, the same thing as the population. The standard error of the sample means would be sigma over the square root of n. Here's the 9.7, and we want to know the probability that it's less than this 1100, that a randomly selected sample of 100 head of cattle, what would be the probability that they're less than 1100? And here's the normal CDF, -1 to the E99, that's out here for the left endpoint, 1100 for the right endpoint. 1135 is the mean. Standard deviation, the standard error of the sampling means would be the 9.7. That probability, here's the e to the -4, so this is times 10 to the -4, or divide by 10 to the 4th, and each one of these would move over. So this is 0.0000154, much less than 0.05. Our criteria for unusual And so it would be unusual for the sample mean to be less than 1100. Here, two standard deviations would be plus and minus 20. So you're only talking about 1105, 1115, up to 1155 would be those plus and minus 2 standard deviations for that. Okay. So this time we basically looked at how to construct the sampling distribution of a sample mean. We did it with the classical version using a tetrahedral die. And then we said how to find the mean and standard deviation of a sampling distribution of X bar. We used the population data of the population mean and the population standard deviation. The central limit theorem told us how to do that, and then how to use this to compute probabilities involving sample means. So I hope that helped. We'll see you next time, and thank you.